Okay, folks, let's go ahead and get started. What I'm going to do today is I'm going to start with a couple of example problems related to what we were discussing on Wednesday, which is the change in the freezing point, the change in the boiling point of solutions, and, well, let me rephrase, the change in the freezing point of the solvent once you've added a solute. The change in the boiling point of a solvent once you've added a solute. And then we're also going to look at a problem where we are dealing with the change in pressure. Now, there are two equations for the change in pressure. If you have a non-volatile solute, then you're just simply going to have the pressure is equal to the mole fraction of the solvent times the original pressure of the solvent. If you have a volatile solute, then the pressure is going to equal the mole fraction of the solute times the original pressure of the solute plus the mole fraction of the solvent times the original pressure of the solvent. So I'm going to start with a few problems of that, and then we're going to get into rates of reaction. Basically, with respect to your exam, after I do these few problems, that is where exam number 1's material ends. So once I get to rates of reaction, that is going to be the start of exam number 2. material. That way you have most of a week to study everything for exam number 1. Okay, so let's look at some examples. Table salt, which is almost entirely sodium chloride, is added to water during cooking in order to raise the temperature of the boiling point. To heat food more quickly. If you add 30.0 grams of table salt to 3.75 kilograms of water, what will be the change in the boiling point of your salt water? KB for water is equal to 0.51 degrees Celsius per molal. Okay, well, the first thing we need to do is we need to get the equation. The equation to figure out the change in boiling point is equal to the molality of our material times KB, and technically times I, though we take I into account in a different manner. Molality, by definition, is equal to the moles of our solute, in this case, our ions, divided by the kilograms of solvent. Okay, so to get to our moles of solute, we need the fact that 30.0 grams of sodium chloride is used. And we need to convert that into moles of sodium chloride. For every 1 mole of sodium chloride, it weighs 50.45 grams. $58.45 grams. Whoops, wrong direction. Now, sodium chloride, if you look at solubility tables, halides are soluble, except for lead 2, mercury 2,2+, or silver. Since this is not one of those, this halide is soluble, meaning that it's going to dissociate into its ions. And we will form 2 moles of ions for every 1 mole of sodium chloride. So we're looking at a mole of 1.0265 moles of ions. The molality, therefore, is going to be 1.0265 moles of ions divided by our kilograms of solvent, which was 3.75 kilograms. So that comes out to be a 0.274 molal solution. Now we can actually get to the answer to the question, which is what is delta TB? Delta TB is equal to the molal, so 0.274 molal times KB, which is 0.51 degrees Celsius per molal. So that is equal to 0.14 degrees Celsius. What this means, folks, water typically boils at 100 degrees Celsius. The new temperature with 30.0 grams of sodium chloride added is going to be 100.14 degrees Celsius. So in other words, it raised it by 0.14. $30 grams really isn't that much. Not for 3.75 kilograms of water. But questions? Let's look at, yes. You will get your solubility rules, yes. I'll try to remember on Monday to bring you a copy of what you'll receive on the exam. And that includes your formulas you'll receive. That includes everything you'll receive on the exam as reference. Okay, so let's calculate the new freezing point of a solution made from 32.7 grams of propane, which is C3H8, dissolved in 137.0 grams of benzene, which is C6H6. The freezing point of benzene of pure benzene is 5.50 degrees Celsius. And its KF is 5.12 degrees Celsius per mole. Okay. So again, we're using the equation delta TF is equal to the molal times the KF, and molal is equal to the moles of solute, in this case propane, divided by our kilograms of solvent, in this case C6H6. So the first thing we need to do is convert that 32.7 grams of propane into moles of propane, using the fact that 1 mole of propane is 44. Yeah, 44 grams. That gives us a value of 32.7 divided by 44, which is 0.7432 moles of propane. Now, why did I not do another step in this conversion like I did in the last conversion? Because it's not a soluble ionic compound. You only have to go that extra step if you're dealing with a soluble ionic compound. Since propane is a covalent molecule, it doesn't dissociate. So the molal is equal to 0.7432 moles of propane divided by kilograms of solvent, which is going to be 0.1370 kilograms of C6H6. Which gives us a molality of 5.42 molal solution. So our delta TF is going to equal the 5.42 molal solution times the KF, which we were told was 5.12 degrees Celsius per molal. So our delta TF is equal to 27.77 degrees Celsius. Now, the original freezing point is 5.50 degrees Celsius. The new freezing point is going to equal that 5.50 degrees Celsius minus 27.77 degrees Celsius. Or in other words, it's going to be negative 22.27 degrees Celsius. Can anybody tell me, on the first problem, I added the change in temperature. On the second problem, I subtracted the change in temperature. Can somebody tell me why? Because the boiling point increases, which was the first problem, whereas freezing point decreases, which is the second problem. Yes. Would you just use that same formula? I was asked if it's changing the melting point, would I use the same formula? And the answer is yes, because melting point and freezing point are the same location. But in the case of melting, I would. You can't actually, no, you cannot use this equation for melting point because you would lower the melting point no matter what. So it would lower it no matter what.
Like in the question, when you say like propane and benzene, and you write the molecule, are you going to tell us those every time?
I will. I also on the test will actually give you the molar masses because you don't have a whole lot of time. So you're getting molar masses to cut out one more step. In fact, I wrote the test today. I will be taking it this weekend and editing it to fit into the 50 minutes because it looks long to me. I will be looking at it, in other words, carefully. But I always write it and then I take it and see what I need to do. Any questions about freezing point depression or boiling point elevation? Huh? Okay. Then let's look at the other vapor pressure. Yes. Boiling point always will increase. Freezing point will always decrease. Okay, let's look at an example problem for the next piece. 30.0 milliliters of pentane which is C5H12 and has a density of 0.626 grams per milliliter and a vapor pressure of 511 torr. And 45.0 milliliters of hexane, which is C6H14 with a density of 0.655 gram per milliliter and a vapor pressure of 150 torr, are mixed at 25 degrees Celsius to form an ideal solution. Calculate the vapor pressure of the solution. Okay. Since we're looking at vapor pressure of a solution, and since I was given two pressures, that means that I am looking at the pressure being equal to the mole fraction of the solute, which is C5H12, times the original pressure of C5H12, plus the mole fraction of C6H14, plus times the original pressure of C6H14. So in order to do this, I'm going to need to get the moles of all of my materials. You have 30.0 milliliters of pentane, C5H12. Pentane has a density of 0.626 grams of C5H12 per 1 milliliter. And since I need that in moles, we're talking about 72 grams C5H12 per 1 mole. So the moles of C5H12 is 0.261 moles. You need to do the same thing for your hexane. We were given 45.0 milliliters of hexane, which is C6H14. Using our density, we can get that into grams, so 0.655 grams of hexane per 1 milliliter of hexane. And then we need our molar mass of hexane. And that is a 14, which is 86 grams of hexane per 1 mole. So it's 0.343 moles. Our total moles which we're going to need is 0.261 plus 0.343, or in other words, 0.604. Now that we have our moles of material, we can actually do the mole fraction like we're supposed to do. So our pressure is going to equal the mole fraction of the the pentane, which is going to be 0.261 divided by 0.604 times the original pressure of pentane, which is 511 torr, plus it is going to equal the moles of hexane, 0.343 divided by the total moles, times the original pressure of the hexane, which was 150 torr. So the pressure of our solution making sure I didn't write anything down wrong, is equal to 306 torr. Questions? Folks, the major trick to boiling point elevation, freezing point depression, and pressure of a solution is knowing your concentration units and how to get to them. That is the trick to it all. And that is the end of test 1 material. So you have almost a full week minus 30 minutes to prep for it. That's one of the things I like to do, is give you plenty of time to prep for a test. So, yes.
I've got a quick question for the problem before that.
Okay, the question about freezing point depression.
Yeah. So I know that the change in the freezing point is the solution freezing point minus the solvent minus the solution. And then didn't we just calculate the solution freezing point?
We calculated the change in freezing point for the introduction of a solute causes to the solvent.
So can I use that equation to figure out, like, moving the things around to know to subtract it? Subtract 5.5 Celsius minus 27.77.
I mean, you can without writing out everything. I just wrote it out so that hopefully it'll make sense when you're looking at your notes. But I don't actually ask you to write out what's what. Okay. So we are now going to get into kinetics. The rest of the semester answers 3 questions. The rest of the semester, save 1 chapter. Well, even that chapter. The rest of the semester answers 3 questions. The first question is answered by kinetics, and that's how fast does a reaction occur. We're going to spend a chapter of information on determining how fast a reaction occurs. The second question that is answered in the remainder of the semester is, to what extent does a reaction occur? And we're going to spend 3 chapters on that question alone. To what extent does a reaction occur when we start talking about equilibrium? And then acid-base titrations. The third question that we will answer this semester is, does the reaction occur in the first place? And that is answered by thermodynamics. And we'll spend 1 and a portion of a chapter on thermodynamics. So we're going to be answering those 3 questions. Today starts answering the question, how fast does the reaction occur? And that is answered through kinetics. So we can start with a very a very general graph that generalizes what occurs on a reaction. Well, even prior to this, but definitely from this point on, if you see brackets around something, that means concentration. And we can graph the concentration versus time. Now, if we think about a reaction, we start out with the reactants. And the reactants, I mean, if we're at the very beginning of a reaction, the only thing that's present are the reactants. And as the reaction progresses, the concentration of the reactants decreases. Initially, it's going to decrease fairly rapidly, but then it's going to level out. Well, this, folks, makes sense if you think about a reaction from a collision standpoint. In order for reactants to combine to make products, those reactants have to collide. Well, when you have nothing but reactants in your solution, it's easy for those reactants to collide. Because that's all they see is each other. They're going to run into each other. But as you progress through a reaction, the amount of reactants decreases. Therefore, what we're talking about is a much lower concentration of those reactants. And the fewer the reactants, the less likely those reactants are going to collide. And because they are much less likely to collide, that's why we see this leveling off effect. We can also talk about a reaction in terms of the products. Initially, there's absolutely no product present. But as time progresses, the amount of product that is going to be in solution is going to increase, and then we're going to see a leveling off effect. Which makes sense because, I mean, if you have fewer reactants colliding, you're going to be getting fewer products. Now, we can describe the rate of reaction based on the disappearance of the reactants or the appearance of the products. Now, just to get an idea of how we can describe this rate of reaction, let's take a very generic reaction. AA plus BB goes to form CC plus DD. Now, reactants disappear. We indicate disappearance with a negative sign. Negative does not mean less than 0. Because let me ask you a question. If I have hydrogen reacting with chlorine to form hydrochloric acid, can I ever get below 0 hydrogen? No. All the sign does is tell you which direction. So signs do not mean below 0. They mean what is happening. A positive sign, the appearance, is indicated with a positive sign. So we can describe a reaction based off of the change in concentration of reactant A versus time. We can describe the change in the reaction in terms of change in concentration of B versus a change in time. We can describe the reaction based on the change in concentration of C versus time. And we can describe the reaction based on the change in concentration of D versus time. Now, to make these things, these changes in concentration versus time, to make A equal to B, we have to take into account their coefficient. So it's actually 1 over A is equal to the negative of 1 over B is equal to the positive of 1 over C is equal to the positive of 1 over D. Again, these pieces that I just added, the 1 over the coefficient, is simply to make whatever's happening to A equivalent to whatever's happening to B, by taking into account their coefficients. Let's look at an example problem. Two N2O gas reacts to give 2 N2 gas plus O2 gas. The first thing I want is I want an equation or series of equations that describe the rate of the reaction based on the reactants and the products. So basically what we're going to do is we're going to do a lot like what I just did with the generic reaction. N2O gets lost because that is a reactant. So it's going to be a negative 1/2 of the change in the N2O concentration divided by the change in time. That is equal to a positive 1/2 for the change in nitrogen concentration versus a change in time. And that is equal to a positive change in the concentration of oxygen versus a change in time. That's what we mean when we're saying express the rate of the reaction in terms of changing concentrations of reactants and products. That's all we're asking you for.
So the lowercase a, b, c, or a, b, c, and d, that's the coefficients of the molecules.
Correct. In the generic reaction, the lowercase a, b, and c are just the coefficients for the reactants A, B, and the product C. Okay, 2. in the first 15 seconds of the reaction, 0.015 moles of oxygen is produced in a reaction vessel with a volume of 0.250 liters. What is the average rate of reaction during this time interval? Okay, brackets means concentration, means molarity, typically. Brackets means concentration, and for the most part, we will be using molarity. Molarity, if you'll recall, is mole solute over liters of solution. So the molarity of this reaction is 0.0115 mole O2 over 0.250 liters of solution. Or in other words, it's 0.06 molar O2. So our rate of reaction, the average rate of reaction is going to equal this 0.06 molar divided by the time, which we were told was 15.0 seconds. Or in other words, it is 0.004 molar per second. Questions about that one?
Like the rate that the concentration goes down per second.
That is the rate that the concentration goes down per second, yes, on average. Yes, so originally it's going to move quicker, and because it said the first 15 seconds. If we had have done it for a later 15 seconds, then it would have been slower. Because of, if you look back at that graph, it slows down. Okay, the third one. Predict the rate of change in N2O concentration. Here is where you go back and you pull off the pieces you need. You need the N2O and you need the O2. Because we've already put this where we've made this equivalency. So going from that equation, the negative of the N2O concentration over change in, -1/2, the change in concentration over the change in time is equal to the change in oxygen concentration over the change in time. So a -1/2 delta N2O over delta T is going to be equal to 0.004 molar per second. Multiplying both sides through by a -2. That means our change in N2O concentration over the change in time is equal to -0.008 molar per second. But here again, negative does not mean that you cannot have a negative concentration. You can never have a negative concentration. What it means is 0.008 molar per second N2O is lost, or I should say 0.008 molar N2O is lost per second. That's what that means. So it comes out as a negative numerical value, but it does not mean negative. It just means that's how much is lost per second. I will pick up, the homework has some of these, and I'll also pick up with at least one more problem on Monday. Then we will get into rate laws on Monday.
No, I didn't.